Yes, welcome to today's video. Today I want us to do some power factor calculations, and with me here is a question, and the question reads that an alternator is applying a load of 300 kilowatts at a power factor of 0.6 lagging, and if the power factor is raised to a unit, how many more kilowatts can the alternator supply for the same kVA loading? So when it comes to power factor, we say that power factor is a very crucial element when it comes to issues to do with power transmission and any other thing that is relating to the power. And again, it also affects the transmission channels, the distribution networks. And now let's see. Now the solution for this one is that first we know that kVA is given by actual power, that is power in kilowatts. You divide by the power factor, that is cos phi. So from there, in this question we are given that the actual power is 300. Then if you divide this by 0.6, this one will give us 500 kVAs, and that is 500 kVAs. So therefore, kilowatt power in kilowatt of a power factor which is 0.6 PF, this one will be 300 kilowatts as stated in the question. So therefore, the actual power at a unit PF will be equals to the apparent power, which is 500 kVA. You multiply by the unit power factor, that is the unit power factor, and this will give us 500 kilowatts. So therefore, raising the power factor, raising the PF to a unit, this one makes our alternator, to operate, or rather to supply power of 500 kilowatts. So therefore, increased power, that is the increased power supplied at unit PF is given by 500. You subtract 300, and everything here should note that it is in kilowatt. So this we have an increase of 200 kilowatts. So to note, once you increase the power factor from 0.6, it now raises our new power to 500, and that increase, that is the increase of the PF, makes our power to increase by a value of 200 kilowatts. So then we can have an example 2, and example 2 says that example 2 reads, we have a three phase 500 kilowatts induction motor, a three-phase 5 kilowatts induction motor as a PF. It has a PF of 0.75, and again it is lagging. Then a bank of capacitors is connected. A bank of capacitors is connected in delta across the supply terminals, and PF is raised to 0.9, again lagging, full stop. So the question says that we should determine the reactive power, that is kVAR rating of the capacitor, that is the capacitors connected in each phase. So just to repeat the question, a three-phase 5 kilowatt induction motor has a power factor of 0.75 lagging. A bank of capacitors is connected in delta across the supply terminals, and the PF is raised to 0.9 lagging. So you are told to determine the reactive power rating of the capacitors connected in each phase. Now again, solution. In our solution, first we need to do a sketch of this system, and in this sketch you realize that it's a sketch of the phasor diagram, and in this sketch there are things that we need to do into consideration. First, we need to consider that the initial phase angle, this one, and we call it cos theta 1. This is what we have been given as 0.75. Then we have another angle here. This is theta 2, and we can say that this is cos phi 2, which is equals to 0.9. Then from this part to this end is whereby we have our actual power as 5 kilowatts. That's our actual power, 5 kilowatts. Then we have point A to point B. Then we have another point here which is named point C, and point C comes as a result of improving the power factor by use of the capacitor bank. So this is our this is the reactive power 2, and it is up to this point C. Then we have our initial reactive power 1. That is the initial reactive power, and this initial reactive power is when we don't have the capacitor in operation. So having done that, now you need to come up with, you identify the given data, and in this case we have a given data in terms of original PF, which is given as cos phi 1 which is equivalent to 0.75, and it is lagging. Then we have the final operating PF, that is final PF of operation, and this is cos phi 2, and this is equivalent to 0.9, and again it is lagging. So again from there we have the motor input. We have our motor input given as 5 kilowatts. Then we have the efficiency, and in this case you can say that this is an ideal case and our efficiency is 100%, and this 100% is an assumed efficiency. We assume that our motor doesn't have losses. So from there we have phi 1, and this phi 1 we obtain it from the power factor, and we simply say that phi 1, the angle, it is cos inverse of 0.75, and from my calculator this one gives an angle of 41.41 degrees. Then we have phi 2, which is again cos inverse of 0.9, and this one will give cos phi 2 of 0.9. This one will give 25.84. So this is 25.84 degrees. So from there we have to get the tangent of phi 1 and phi 2. So tangent of phi 1, which is equivalent to tan of the angle, that is 41.41 degrees, and tangent of 41.41 gives 0.8819. Then we have tangent of phi 2, which is equivalent to tan of 25.84 degrees, and this one is, so if we edit this, we put 25.84, this one gives 0.4843. So from there we look for leading reactive power taken by the condenser bank, or that is now the power that is taken by our capacitors. So this is given by the actual power P into tangent of phi 1, you subtract tangent of phi 2, and we know that tan phi 1 and tan phi 2. So we have our power as 5 kilowatts, so we use 5 into tan phi 1, that is 0.8819, you subtract 0.4843, and this will give you, so this is 5 This is 5 multiplied by into bracket 0.8819 minus 0.4843, close the bracket. This gives 1.988 kVAR, that is reactive power. So therefore, to get ratings, this is rating, to get rating of capacitors, connected in each, to get the rating of capacitors connected in each phase, it is simply the leading reactive power taken by the capacitor bank. That is the total. So before we go to that, let me explain something here. This is if these are our three phase, then we have our delta capacitor connected here. That is our delta capacitor connected condenser. So we have that phase, and again we have this, then there is this here coming to that downwards. So if this is our motor, that is our motor. So the power that we have in here, this power here, it is simply the total power for the 3 amps. So that is the total power for the 3 amps. Now to get the capacitor, the rating of each capacitor, that is the individual capacitor, it is this power divided by 3. So rating of each capacitor connected in each phase is given by 1.988, you divide by 3. So 1.988 divided by 3, this gives a value which is 0.66267 kVAR. So this is approximate 0.663 kVAR. So let's look for another example, example 3. Example 3. Now in our example 3, it says that a single phase motor connected to a 400 volts, 50 hertz supply takes 50 hertz supply takes, this one takes 3.7 amperes at power factor of 0.7 lagging. So we are told to calculate the capacitance required in parallel with the motor to raise the power factor to 0.9 lagging. Calculate the power factor required in parallel with the motor to raise the power factor to a lagging of 0.9. So first, on the solution for this, first a small sketch. We do a small sketch. So this is our motor here. And we have our supply, which is 400 volts, 50 hertz. So this is the capacitor. The value of this capacitor is what we are looking for. We are looking for the value of this capacitor, and we have our motor current here, IM, as that 1.7 amperes. So therefore, we need to again sketch the phasor diagram. We need to sketch the phasor diagram, and in this case, our phasor diagram will look like this. Our phasor diagram will look like this. So let me use my pen here to help me. So this is how our phasor diagram will look like. Then we have this point here, and we have this point again here. So we have another point over there. So this is our point A, and we have another point like that. We have that point. Then we have this angle here, and this is our angle phi m. That is the phase angle for the motor. Then we have our current here, IM. Then we have our normal current, that is the normal circuit current, and that current I here, it is the current that is supplied before you connect to a capacitor, or the current before the capacitor connection. Then we have our voltage, that supply voltage. We have this angle, which is 90 degrees. That angle is 90 degrees. Then we have our initial angle phi. That's our initial angle phi, and that is the angle between the voltage and the current. So this angle phi it is the phasor angle at our initial current, that is between voltage and our initial current. Then the angle phi m, this is the angle after you've connected your capacitor. So phi m is the angle after connecting your capacitor, and it gives the relationship between the motor current Im and the supply voltage V. So from this, we need to look at a few things, and one is active component of our motor current Im, which is given by Im cos phi m, and in this case it is 31.7. You multiply by the power factor, which is 0.7, and this one will give you a current of 22.19 amperes. Then we get our active component, of I, that is the initial current, given as I cos phi, and this is simply equivalent to I multiplied by 0.9, which is equivalent to 22.19 amperes. So that means we need to get the value of I. And getting the value of I simply means we make I the subject, or we substitute for I. So that implies that I is equivalent to 22.19. You divide by 0.9, and 22.19 divided by 0.9, this one will give you 24. So this is 24.6556 amperes. Then from there we get our reactive component of Im, that is the motor current after you've connected your capacitor. So this is simply equals to the current Im, you multiply by sine of phi m. So remember, in this case we are using sine of phi m, and the reason why we are using sine of phi m is because the reason I was saying, the reason why you're using sine of phi is because now in the Cartesian plane we are dealing with the imaginary part. This the reactive component is always found on the imaginary part of the Cartesian plane. So this is simply equivalent to that 1.7 multiply by, now our sine of phi will be given by 0.7141, and this 0.741 is simply coming from, if you take the square root of 1 squared minus 0.7 squared. Now remember, 0.7 squared was our initial PF, so this one will give you, that is the square root into 1 squared, you minus 0.7 squared, squared, close the bracket, this will give you 0.714. So you say now it is that 1.7 multiply by 0.7141, and this gives you 22 point, so this is equivalent to 22.636 and 697 amperes. So again we get reactive component of I, which is given by I sine of phi. So we know our I as 24.6556. So we multiply by the square root of 1 squared minus 0.9 squared. So this is 24.6556 multiplied by 0. So this is 0.436 if you compute this one here, and now this gives you a value of, so you have 24.6556 multiplied by 0.436, which will give you 10.749, and again this is amperes. So from the phasor diagram, we can find our capacitor current IC, and this is simply equals to reactive component. This is simply equals to the reactive component of IM. You subtract the reactive component of our supply current I. So this is 22.6 63697 minus 10.7498, and now this is 22.63697. You subtract 10.7498, and this will give you 11.88 11.887 amperes. Now from there we know that our current IC can be given by voltage, everything divided by the reactive capacitance, and this is simply equivalent to voltage multiplied by this voltage multiplied by 2 pi fc, that is 2 multiplied by the frequency multiplied by the capacitance. But remember, you are looking for this capacitance C. So therefore you can say that this is equivalent to 11.8872 is equivalent to our supply voltage is 400 volts. You multiply by 2 pi multiplied by our frequency 50, we multiply by our capacitance C. So we are looking for C. So if you make in C the subject, that is making C the subject, we simply say that C is equivalent to 11.87, that is 8872, you divide by 400 multiplied by 2 pi multiplied by 50. So if you simplify this, it will give you, so let's simplify calculator. So you have 11.872, you divide by into bracket 400 times 2 times 50 close bracket. This gives something we've missed out, so let me correct. So we have to multiply by pi, and this will give 0.00094595. So therefore we can simply say that our value of capacitance C is approximately 94.59 microfarads. So this is the value of our capacitor that is required now to raise our PF from 0.7 to 0.9. So from there, let's look at another example. This is example, I believe this is example number 4. Example 4, and it says that a single phase AC generator A single phase AC generator supplies the following loads. So one is that we have a lighting, supplies a lighting load of 20 kilowatts at unit PF. Then two, it also supplies an induction motor load of 100 kilowatt at 0.707 lagging PF. Then three, there is a synchronous motor load of 50 kilowatt at 0.9, and this synchronous motor is just a leading PF. So now the question says calculate the total apparent power in kVA delivered by the generator and PF at which it works, So solution. First, we need to calculate the initial apparent powers that are being supplied. Starting from our lighting load. So that is, we have kVA 1, which is, now we take the true power of load 1, you divide by the power factor phi 1, and this is simply 20 divided by 1 because the power factor is a unit, and this gives you 20 kVAs. Then we move to load 2, which is true power 2, the active power of load 2, you divide by the power factor, that is cos phi 2, and this is 100 divided by 0.707, and this gives you, so if we divide this, will give you 141. So this is 141.443 kVA. Then we move to load 3, which is actual power 3 divided by cos phi 3. So this is again 50, you divide by 0.9, so you have 50 divided by 0.9, and this gives 55.556 kVA. Now from there we need to sketch. We need to sketch the relationship between all these, the actual power, the apparent power, and the reactive power, and also show the relationship in terms of, we show the relationship in terms of the power factor. So in short, it's like we are plotting a Cartesian plane to actually bring out the relationship. So I'm going to do a sketch, and in this sketch is what I will use to calculate the reactive power at all the three stages. So we have this moving direction, then we have its counterpart, which is dotted, and the other side is also dotted. Then we have another one here, which is also again dotted. So this is voltage, and this is current. That is our voltage and current. So we have the origin here, which is 0. So this side is treated as positive, then we treat this side as negative. So we will have a power here, which is kilowatts 2, and we have another power here, which is kilowatt 3, and we have this power. This one here is kVA1, equivalent to kilowatt 1, equivalent to kilowatt 1. Then we have this angle here, and that angle is phi 2 being equals to 45 degrees. Then we have this line moving this way as our kVA 2. Then we have this one here as our kVA 3. So remember our kVA 1 is here, our kVA 3 is here, and our kVA 2 is here. So that now represent all our loads. So in most cases this one will be our induction motor. That will be our induction motor. And this one here will represent our synchronous motor. Then we have an angle here, and that angle is our angle phi 3 given as 25.83. So in our synchronous motor, it is operating at a power factor of 0.9. So therefore, if we get the angle, that is cos inverse of 0.9, cos inverse of 0.9 gives us 25.84, which is close to this. And again, our second motor, that is the induction motor, operating at a lagging power of 0.707. So again, if we get the angle 0.707, this gives us 45.0086, which is this angle here. So that's why I indicated this one as our induction motor load. Then we have our lighting load at a unit power factor. So in most cases, the vertical line here, this represents our lighting load. So that one represents our lighting load. And the power factor is a unit power factor, so it is the cos inverse of 1 to give you 0 degrees angle. Then something interesting here, we know that in power factor, if you get a positive value, the power factor is low. In other words, we have our third load with the leading power factor, so automatically it is a positive. So on this side we have kVAR 3 and we have kVAR 2. So remember, this is a negative sign signifying a leading power factor. So from there, we need to calculate the following elements. So the first one is reactive power, kVAR 1, which is equivalent to apparent power, kVA 1 sine of phi 1, and this is equivalent to, we had our first apparent power as 20 kVA, so this is 20 multiplied by sine phi. Our angle is 0, so our sign will be this sine phi 1 will be equivalent to 0, and this gives 0 reactive power. Then we have kVA R2, which is given by kVA 2 sine of phi 2, and this is equivalent to, now this power from the diagram here, we have seen that it is lying on the negative side, so this now becomes negative 141.443. We multiply by our sign. So again, we'll do the reverse of it. So we'll take this as root into 1 square minus 0.707 square, close the bracket, and again this will give you 0.707. so if you multiply the two, so multiply by negative 141.443, this gives you negative 100 kVAR. Then we have our third reactive power, which is equals to kVA 2 sine phi 3, and again this is this power, the reactive power on this side, and with the guidance of this sign, this now becomes plus 55.556, we multiply by the square root of 1 squared minus the given PF squared, that is 0.9, and again this gives, so this is 55.556 multiplied by the square root into 1 squared minus 0.9 squared, close the bracket. This gives 24.216 3 kVAR. So something you should note here is that an NEB, that kVAR2 and kVAR3, these ones are in opposite, they are flowing in the opposite directions of each other, so they're in opposite directions, and therefore we have kVAR2 being lagging and kVAR3, this is leading, that is our leading kVAR, that is our leading reactive power in short. So from there we can calculate our total power, and actually our total power comes from the initial power that was given. So the total power will be summation of the lighting load, that is the actual power of the lighting load, plus the induction motor load, plus the 50 kilowatt load for our synchronous motor. So therefore the total actual power so we get total actual power, this is kilowatts, this will be 20 plus 100 plus 50, and this will give 170 kilowatts. So again from there we get total reactive power in kVAR. This will be 100, not 100, 0 plus minus our second reactive power, that was negative 100, plus 24.2163. So this is 0 plus minus 100 plus 24.2163. This gives negative 75.78, negative 75.7837 kVAR. Now from there we can say that from there we can have a relationship in this form. Now this is where we have our actual power, 170 kilowatts. So on this side we have our reactive power, which is negative 75.7837, and this is our kVA, that is apparent power. So this is our apparent power, and we can simply say that total apparent power in kVA is equivalent to total power, that is the actual power, squared, you add kVAR, that is the reactive power, squared, and this will give 170 squared plus negative 75.7837 squared. And now kVA, our kVA now becomes, so we have root of 170 squared plus 75.7837 squared. So this becomes 186.1268 kVA. And this is approximate 186 point, let's call it 186 0. Let's call it 186. That is to the nearest whole number, and therefore power factor is equals to total power in kilowatts, you divide by total power in kilovolts ampere, that is kVA. So in other words, we are saying this is true power, you divide by apparent power, that is true power divided by apparent power. And this is simply equivalent to 170 divided by 186, and this gives you, so we have 170 divided by 186, this gives you 0.9139. So this is approximate 0.914, and it is a positive, so it's a positive, so that means it's a lagging PF, that is a lagging PF, that's a lagging PF. So you can therefore say an NB and say that the PF must be lagging since we have a resultant reactive power. We have a resultant reactive power being lagging. So that makes our PF to be lagging. So the question was asking, if I may go back here, the question was asking that we calculate the total kVA and delivered by the generator and the PF at which the generator works. So that is our total kVA is, so total apparent power kVA, this is approximate 186 kVA as you have calculated it here, and our PF is, this is cos phi 1 or cos phi nu. Cos phi nu is now equivalent to 0.914 and it is lagging. So those are the two required values and it is lagging. Now from there, we can have a short break, that is a very short break, and we can get to look at something else something else. And guys, I also teach mathematics, and one of these fine days I'll take you through mathematics and explain some basics in mathematics. So let's do another example. That is an example 3, not example 3, example number 5. Example number 5. And our example reads, or rather says, it says that our other example says that it says that a 3-phase motor, that is a 3-phase, let me try this pen, it's green in color. So we have what is this visible? We have a 3-phase, that is not visible. So we have a 3-phase 50 hertz, 3-phase 50 hertz, 400 volts, 400 volts. Just a minute. So we have a 3-phase 50 hertz 400 volts motor develops 100 horsepower. It develops 100 horsepower, that is HP, comma, the PF is 0.75 and it is lagging. 0.75 lagging, and efficiency of 93%. Then a bank of capacitors is connected in delta across the supply terminals, and PF raises to 0.95. The PF raises to 0.95. So the PF raises to 0.95, lagging. So each of the capacitance units is built of 4 similar 100 volt capacitors. So you are told to determine the capacitance of each capacitor. So let me read the question again. It says a 3-phase 50 hertz 400 volts motor develops 100 HP, that is horsepower. The PF is 0.75 lagging and efficiency of 93%, full stop. A bank of capacitors is connected in delta across the supply terminals and the PF raised to 0.95 lagging. Now each of the capacitance unit is built of 4 similar 100 volts capacitor. Determine the capacitance of each capacitor. Each of the capacitance unit is built of 4 similar 100 volts. So on our solution, first we need to identify the given data. You realize that this question has a lot of data. So the first one is motor output, which is given as 100 HP. And 100 HP, we know that 1 horsepower is equivalent to 746 watts. So therefore, with the 100 HP, it simply means it is 100 multiplied by 7. This is 100. You multiply by 746, you get 74.6 kilowatts. So our motor is 74.6 kilowatts. Then we have a original PF, that is cos phi 1, and this is 0.75, and it is lagging. So from there, our final operating PF, that is cos phi 2, which is 0.95, and again it is lagging. Then there is the motor efficiency, and in this case is given as 93%. So from there, we can get our motor input, which is given by motor output. You divide by motor efficiency, and this one is simply 74.64. You divide by 0.93. So if we do the tabulation in a calculator, this 74.6 divide by 0.93, this gives you 80.215 kilowatt. So this is approximate 80 kilowatts. Well, that's approximately 80 kilowatts. So from there, we have our phi 1. Which now the angle can be given by cos inverse of 0.75, and this cos inverse of 0.75 this is 41.41 degrees. Then we get tangent of phi 1, which is tan 41.41, and this will give us 0.8891. So again we have phi 2, which is cos inverse of 0.95, So cos inverse of 0.95, this is 18.19 degrees. So we get tan phi 2, which is equals to tan 18.19. So tan 18.19, which gives 0.3286. So from there, we need to come up with our leading reactive power. Taken by the condenser bank, and this is given by the actual power P, tangent of phi 1 into tangent of phi 1 minus tangent of phi 2. So this is 80, the actual power, into tangent of phi 1 is 0.891 minus 0.3286. So again, this is 80 multiplied by into 0.8819 minus 0.3286, and this one gives 44. This is 44.264 kVAR. So from there, again, we calculate leading reactive power. Leading reactive power taken by each of 3 sets of capacitors. 3 sets of capacitors, and that is simply the total power here, which is 44.264. We divide by 3 because we have 3 arms. So answer divided by 3, this gives 14.75 kVAR. kVAR. So again, we call this our equation 1. Call that our equation 1. And from there, now we need to come up with a sketch or something that is relating closely to what we are doing. And I believe it will fit here. So with my sketch, I have the capacitor arms. So you are being told each arm is a delta connection, with each arm having 4 capacitors. So that's how we come up with our sketch. So we have this one connected to that directly, then we have this point connected to that one directly. So we have this one, it is jumping, then it is jumping, then you connect it to this one. So this is our 3-phase motor here. That is our load, our 3-phase motor there. And we are told that the supply in between here, and this is our supply load. The supply voltage, which is 400 volts, and it is line to line. So from this line to this line it's 400, or from line to this line it's 400. So it is line, it is 400. Then we have our current, that is our capacitor current, the current ICP, that is the capacitor bank current flowing in that direction. So this is ICP again, and again here we have our ICP. So those are our currents, and from those currents we know clearly that current ICP is equals to the phase voltage you divide by reactance capacitance, which is simply is equals to 2 pi f multiplied by the capacitance, you multiply by the phase voltage. So we can simply substitute some values on this side. So this is 2 pi multiplied by the frequency, which is 50, multiplied by 400, the phase voltage, multiplied by the value of the capacitance C, which we don't know for now. So we are looking for this value of this capacitance. So this is 2 multiplied by pi multiplied by 50 multiplied by 400, which gives 125,663.7061 C. C stands for capacitance. And we can simply say that this is approximate 125,600 multiplied by C amperes. For now you can call it amperes. So from there we can get reactive power per phase, that is reactive power per phase, being given by phase voltage multiplied by the current of the capacitors divided by 1000. 1000 is to simplify the many zeros, and this is 400 multiplied by ICP, and we know that our ICP is 125,600 of C. You divide by 1000, so cancel this. So we have 40, times 125 6. This gives 50 240 C. So we call this equation 2. Remember we had equation 1, so that's our equation 2. So therefore, equating equation 1 and equation 2, you simply say 50 240 C is equivalent to the value that we had for equation 1, which was 14.75. So if we equate the two, this is 14.75. So we can simply say that C is equivalent to 14.75 divided by 50 240. So we have 14.75 divided by 50 240 to give you a value which is 0.0002959 farads. So we can simply say this is approximate to 1 2 3 4 5 1 2 3 4 5. So this is 293.59 microfarads. So now since our combination in each arm it includes 4 capacitors, so that means the capacitance of each capacitor. So capacitance of each capacitor is equals to 4 multiplied by 293.59 microfarads. This is 4 times 293.59. That gives you and there's something you're forgetting here. So multiplied by 10 to power -6 and again now this gives an approximate value of 1174.36 microfarads. So that is the value of the capacitance in each of the arm. So it simply shows that if you have these capacitors here, if you have these capacitors, so 1 2 3 4, 1 2 3 4. So it simply means that in this arm you need a total capacitance of 1174.36 microfarads, And again on this other arm you require 1174.36 microfarad, and the same case applies here. You require 1174.36 microfarads. So that's all for those few examples that we have done, that we have looked at, and I wish that you subscribe. Let us learn more. Subscribe, share, comment, tell a friend, and keep watching. Thank you, and God bless you. Bye bye for now. Let's meet next time. Thank you.